So here's, and actually I've used this worksheet before. So this is what we had in class from the, let me share screen. There we go. Okay, so this is what we had in the lecture notes describing how we can label nodes, and it kind of matches what I discussed the other day. Always recommend labeling nodes where we draw, you know, anywhere where there's not a drop. So there's no drop there, so that's all one node. Everything here, there's not a drop, so it's all one node. I'm going to change my marker to blue. And so for this first one, the three nodes that we're looking for, there's an A is where the node begins. Here is all one node. And if you're kind of following along the lines, you can see it goes all the way around. That's all B, right? Everything inside of this wire, everything, all of that is B. It's kind of messy looking. But we don't have any voltage drop anywhere in between there. And then here's C. So if I'm doing my equivalent equation, my R equivalent or R total for this, here's a notation thing, is the way it says R total with an arrow. What that means is that starting from one side of it to the other side of it. And so that's why, so someone had asked, are these all in parallel? And they would be if we connected these with just a wire, but then you wouldn't really have a circuit because you'd have no source. You're just looking at resistors. So when we're doing R total and we put an arrow, and that'll come in handy later this week, especially on some of the other topics, but when we put R total with an arrow, it means as if we started here and then ended here, right? And so even like with the little way that the current stuff works on the circuit simulator, right? It's like the current's flowing through that all the way back to here. So it divides here. So R1 and R2 are in parallel with each other. They each share A and B on the outside. And some of y'all, if you're struggling with seeing what is parallel or seeing nodes, A and B are what is outside of R1 and R2. And I've had some students that were struggling with it just often label their nodes with like A and B are my parallel elements just to keep track of it. And then B and C are the nodes on the outside of R3 and R4. And so you can see there is this node shared, B is in the middle of these two together, which makes them in series. So if you wanted to just write one R total equation, right, that's a way to simplify the shortcut equation. Another way to do it is with the box method. So if you wanted to put R1 and R2, so I'm going to clear all the drawings out. Wanted to put R1 and R2 in a box like that and say R equivalent for those two and then solve for it and kind of redraw it as you go. That's another way to do it. And then R3 and R4 are in parallel, so they go in the box. For this one, I do have just 2 extra steps in my explanation, but it's not any different of a problem. And so the extra steps just first is labeling nodes. Here's A, here's B, here's C, and then this is just one node, right? There's no voltage drop. This is just a wire. So even though it might have said C and D on your example problem, it's really just one node. So I think most everyone was getting the R equivalent on the rooms I was checking in, which is that 10 is in series with this, the dividing is here. So 20 and 40 are in series. That's in parallel with a 30 right there. And then that all together, actually, yeah, so R equivalent, if we're just finding R equivalent, would be 20 ohms. R equivalent from where this one starts at B. And then if the R total, we would add in the 10. And so here's an example of that box method. Here's everything inside the box. All together makes 20. So there's the box again, right? And so that's the R equivalent, whereas 10 and 50 on the outside of that. And so I can put those together and get my R total is 80. And so the 80 volts divided by 80 ohms gives us 1 amp. And then here's where it gets a little bit tricky. So go into this R equivalent, right? And the R equivalent that we had you solve for up here in this 20, that is the R equivalent that goes on top. And then the Rx is everything from the node of dividing. Well, where does it divide? I'll put it in red. It divides in node B and it rejoins in this node down here. So if I'm looking for I2, here's I2 going through there. It's everything between the node of dividing to the node of rejoining. So it's 60 ohms, because here's I2 down here, right? And you can even see I've kind of written R total between the nodes and the R of the branch between those nodes. And the I is the I being divided. So in this case, it happens to be I total. You could have a case where you can divide the current that isn't I total. In this circuit, I total is what is going into B. And so therefore it is the I equivalent. And notice that this R equivalent doesn't include the 10 and it doesn't include the 50. And that's because they're before and after the node of dividing and the node of rejoining. So if we are using VDR to solve this one rather than CDR, then if we think that we need series elements in order to use VDR, then what we're doing here first, if we're trying to get to R4, right, that's the goal. Well, what is in series with R4? There's one node exclusively shared. Only 3 is in series with 4, right? Otherwise, there's this other parallel element. So I have to kind of use 2 times where I use VDR. So the first one, and here's an example of where redrawing helps, is if I redraw and I simplify all of these into one equivalent resistor, that's this right here, right? There's the box. And so those together make 30. And so I've put this 60 in series with 30, and I can do a VDR to find a drop from B to D, right? And then the Rx in this case is 30, the R equivalent is 60 plus 30, and the voltage source is the total. So that would give me from B to D. Now the second VDR that we can do is if I am going from B to D, well, what are my series elements from B down to D? It's the 10 and the 30. So the R equivalent in this case is 40, right? That's the 30 plus 10. And then the Rx is what I'm solving for, which is just right here, the R4. So someone asked another way to do this, and that gives you at the end 30 volts, right? There's 30 volts. So another way to do this, if we didn't say specify VDR, you could do current divider rule, right? Here's where the current's dividing in this node and it's rejoining in this node. And then once I know this current, call it I2, I can multiply I2 by 30, and that would be V equals IZ, that's Ohm's law. And so that's another way to solve it. But if it said VDR, that's the best way to do it right there. But if you got to 30 volts and your equations make sense, it's possible to get it other way.